Alright guys, welcome back to Underground Science, and in this video we're going to be talking about hydrogenation. So we're starting the reactions unit of organic chemistry, and so the most basic reaction that we should know is hydrogenation, and it's kind of in the name. So hydrogenation is basically adding hydrogen atoms across a double bond. You can also add hydrogen atoms across a triple bond, but in this case we're just going to be talking about alkene hydrogenation. So across an alkene, okay, specifically we're going to be talking about double bonds in this video. And so if we jump into an example right away, let's say we had a molecule that looked something like that, and we said, okay, we're going to add hydrogens across it. But for this reaction to actually go through, we need an enzyme, so we have to lower the activation energy, right? And we'll go over that in our general chem videos when we talk about thermodynamics and everything. But an enzyme basically helps the reaction go quicker, and it lowers the activation energy, so it's easier to go from reactants to products. So the enzyme we're going to use, or the catalyst in this scenario, will be palladium with carbon. And so what this will do is, if we bring this down here, this is basically a hydrogen bound to a hydrogen. So palladium on carbon will come here and cleave the single bond right between the two hydrogens. And so you're going to have two individual hydrogens now, 1 and 2. And then these two hydrogens, the palladium on carbon, with the help of palladium on carbon, these two hydrogens will attach onto each side of the double bond on this carbon and on this carbon. So the product is going to look like this, and the double bond used to be here, but because you added hydrogens on it, the double bond goes away, because now this carbon and this carbon has 4 bonds, so that's why the double bond goes away, and those hydrogens get put over here. So another way to write this product, or draw this product I should say, would just simply be like that, because remember, in a line diagram you don't have to show the hydrogens off a carbon. So then this would be your answer. Alright, so if we go to another example that's very similar to the previous one, and if we drew this and we said, okay, let's do, as soon as you see hydrogen gas with palladium on carbon, right, or any catalyst, then you should immediately know, okay, we have hydrogenation going on. So right away you should know, okay, these two hydrogens will be added on to each side of the double bond. So the carbon here and the carbon here, because these two carbons are involved in the double bond. So one hydrogen goes here, one hydrogen goes here. And if you put one hydrogen here and one hydrogen here, the double bond goes away, because right now, as of now, this carbon has 1 bond to hydrogen, right? Because each carbon can have 4 bonds. So this carbon has 1, 2, 3, 4. And then this carbon only has 2 bonds right now, but if we draw how many hydrogens it has bound to it, it has 2 hydrogens bound to it. Okay, so that means that if you put 1 hydrogen over here, right, and 1 hydrogen over here, you can't, because if we didn't remove the double bond, then it would be like this. We would have 2 hydrogens, right? Let's say you added the hydrogen orange, right, in the reaction. You added the hydrogen orange, and then we kept the hydrogen that's already on there, and then we added 2 hydrogens were already on here, but then we added another hydrogen, right, and previously we already had a double bond here. Like, if you didn't remove the double bond, this carbon would have 1, 2, 3, 4, 5 bonds, and this carbon would have 1, 2, 3, 4, 5 bonds. Carbon can only have 4 bonds. You can't have 5, that breaks the octet rule. That's why the double bond disappears. Okay, so now each carbon has 4 bonds, 1, 2, 3, 4, and this one has 1, 2, 3, 4. Alright, so this would be your answer right here. So if we drew the molecule in, we can, if we're just drawing a line diagram, you can simply draw that. Alright, if we go to another example, right, this example, let's say we have a cyclic compound involved. So if we drew something like that, and then we're reacting it with hydrogen gas and a good catalyst like palladium with carbon, this will lead to the same product, right, or the same idea, which is this double bond goes away because we add hydrogens across the double bond. But specifically in this scenario, right, especially if we're dealing with cyclic compounds like this, in hydrogenation, one thing we should know is that this involves syn addition. We'll go over stereochemistry later, but basically what we should know is if you see a bond, right, that's represented as a wedge, this indicates that the bond is coming at you. Okay, so this is when we're talking about 3D. We're talking about 3D molecules. So if you see a wedge bond, right, something like this, that means that that bond is coming at you. Okay, and if you see a dash, right, a bond represented by a dash, this means that that bond is going away from you. Going away from you. So into the screen, going away from you. Okay, so knowing that, if this cyclic compound, right, this cyclic compound has on these two carbons that's involved in double bond, it has an ethyl group coming off of it and a propyl group coming off of it. So that means that these two will either be, like when you add the hydrogens on, it's syn addition. This means you're adding both the hydrogens, either both on a wedge or both on a dash. So what that means is you're adding both hydrogens either coming at you, right? Or you're adding both hydrogens so that it's going away from you. So either it's going to be like this, you're going to add both the hydrogens like this on a wedge, right? Or you're going to add both the hydrogens like on a dash. Okay, so that means there can be two possible products. So let's draw the two products. So what did we have? We had this as our reactant, and then we had hydrogen gas with palladium on carbon. So we said the hydrogens will always add on the same side. So either both the hydrogens have to be on a wedge or both the hydrogens have to be on a dash. So one possible product will be like this, like that, and then we're going to have, so the ethyl substituent will be like this, and so will the propyl substituent, and we'll see why in just a second. And then the hydrogens will be on a dash, or the other product can look like this because the hydrogens can also add so that both the hydrogens are on a wedge bond. So that means that the substituents will then have to be on a dash because again it's syn addition. So you can also have the substituents like that, and then the hydrogens will be on a wedge like that. All right, so this represents syn addition. And why is it syn addition? Again, because both hydrogens are adding on the same side. So either both hydrogens will be adding onto this molecule so that the hydrogens are pointing away from us because it's on a dash, or both the hydrogens are adding on the molecule so that the hydrogens are coming towards us, which means they're both on a wedge. You can't have one on a dash and one on a wedge because that's not syn addition, that would be anti-addition, which we'll see later. Okay, so this is syn addition. And last but not least, if we again do an example, this one shouldn't be that hard because this is actually a cycloalkene to a cycloalkane conversion, because if you do hydrogenation on a cycloalkene like this, right, with palladium on carbon, you'll actually add hydrogens across this double bond here, which will lead to the product, which will look like this, because the hydrogens got added on across this double bond, so the double bond goes away. So now we're left with the cycloalkane. Specifically though, this is a cyclohexene, and you convert that to a cyclohexane. All right, and so this is basically hydrogenation, catalytic hydrogenation, because you need a catalyst, palladium on carbon. And in the next video, we'll start talking about hydrohalogenation, which shouldn't be that hard once we go through the mechanism and really dive into it. All right, so I hope to see you guys there.